Okay, so with Turing machines, the deal is this. It's good. Some problems you can basically solve in a very simple way. For instance, and you know that there's an answer to. You can say that, well, if you're not an amputee, you have 4 limbs, and so if you have 5 people, then you have 5 times 4, and so that will be 20 limbs. You don't actually have to count the limbs. 1, 2, 3, 4, next person, 5, 6, 7, 8. You can essentially use a simple equation and come up with the answer. There are other problems where you're not able to come up with a simple equation. What you need to do is run the program. And of those types of problems, there are some problems which you know you can come up with an answer, and there are other problems where you don't know if you can or not. In other words, some you can say, well, eventually this Turing machine, this computer, will give us an answer, and another one will say, well, we don't know. And the only way to know is to run it until you get an answer, and if you don't get an answer, you don't know if there is or is not an answer, because you would have to run the machine infinitely long to know if there was an answer. So that's kind of a cool question. That's part of what happens in number theory. There are certain propositions in number theory in which we don't know if we're going to be able to come up with an answer or not, and then the machine would just keep running. I ate breakfast at 9, and it's now noon, and now I'm hungry, and I should have thought of that before I made the video. But anyway. Okay, so how does this relate to other jazz? Well, back in the day when we thought the universe was like a clockwork, we thought around the end of the 1800s that just about all science was wrapped up, and there were just like a few little details to work out. And those details led to an explosion which ended up in the development of relativity and also into quantum mechanics. And so this whole deterministic notion was kind of gone in quantum mechanics, which is based on probabilities. But as far as relativity was extremely deterministic. The only thing that was different about relativity is we learned that time is not absolute. It changes depending on your reference frame, and so space is the same way, and mass and energy and length and momentum and all these things, but the whole system was deterministic. And Einstein believed in a clockwork universe, and the way he came up with relativity was just assuming that light was going to be an absolute, the light speed, is going to be absolute, and then everything in relativity follows from that. And what's interesting is you end up with some very non-commonsensical notions about the world, but it all fits together really nicely. But Einstein's prejudice was for deterministic universe. Ironically, in 1905, when Albert Einstein discovered the photoelectric effect, explained the photoelectric effect, Planck did the earlier work. The irony is that Albert Einstein received the Nobel Prize for the photoelectric effect, and of course he spent the rest of his life fighting against the notion of quantum mechanics, which is the idea that things exist as probabilities. And I want to tell you my own personal prejudice about science, and the way this works is it's kind of like investing, is that past performance does not predict future results, so that Einstein may have preferred a deterministic universe, and I may be turned on by a very Baroque universe, but you never really know which way it's going to be. But human beings, they have their passions, their feelings about the way they think the universe should be. Einstein, by the way, believed that God, Einstein was a deist. He believed in a God, Spinoza's God, that created the universe and then had nothing else to do with it. But Einstein believed that God had no choice but to create the universe he did. And of course, in quantum mechanics, one possible interpretation of quantum mechanics is the many worlds hypothesis, which banana time. The many worlds hypothesis by a graduate student of John Wheeler, a big famous guy, Hugh Everett, came up with. And in quantum mechanics, essentially what happens is, if you have, let's see if we can get these on camera, yeah. If you have two photons, particles of light, and they interact, what happens to this is there's something called quantum entanglement. And they carry essentially a memory of this, this meeting here. And when they go out their separate ways, it turns out that what you do on this photon over here has an immediate effect on this photon right over here. And it's been proven, see Bell's theorem and the Allen aspect experiment, it's been proven that there are no hidden variables. In other words, those photons exist in a quantum state where they do not have actualities, just probabilities. And it's been statistically proven by very simple math. All you need is just algebra. And it's been proven that they don't actually have a state that's hidden. That state doesn't exist until there's a measurement. Now, what Hugh Everett came up with is the idea that every time there's a quantum event, that essentially the universe splits into two or more different universes. Now, people said, well, that makes everything fine, but it's awfully bizarre having all these universes. But there's another way to look at it. You can look at it from the standpoint of banana time,